red line. So this means it's a more radiation dosage is required for tissue damage. This phenomenon does not occur in the solid line tumor cells. The flash effect has already been evaluated in many tissues using many types of radiation sources. Most of these studies have used tissue inflammation and tissue damage as endpoint. For example, studies have shown that irradiation to the brain resulted in the reduced inflammation and keep on the mouse's memories. So compared to the conventional dose rate radiation, or skin lung, lung and skin. So inflammation was also reduced compared to conventional dose irradiation. These findings were well known in the field. So one of the initial hypotheses is the oxygen depletion. In ultra-high dose rate irradiation, the ionization and excitation density is much higher than in normal dose rate irradiation. So the supply of the oxygen that should originally be used for post-irradiation chemical reactions cannot keep up, resulting in the situation where oxygen is not available for some chemical reactions. The theory is this result is the same situation as the hypoxic environment. Hypoxic environment occurs a radio resistance, as you know, and the cell survival rate is higher. So here is one of the paper result of the experiments on the mice using the flash electron beam. So indeed, it can be seen the biological oxygen level of mice exposed to flash irradiation. Also, just a moment. So this, yes, flash irradiation. So decrease the oxygen level, so at momentary. However, so this decrease oxygen concentration does not explain why tissue damage is suppressed in the mice, and it's believed that other factors also involved in the suppression of the tissue damage. So when the radiation is delivered over the very short time, is extremely very very high dose rate. As in the flash radiation, radicals are generated locally at a very high concentrations. Under such high density condition, the rate of the radical generations exceeds the rate of the which intracellular oxygen can be consumed. As a result, so radicals are more likely to react with each other, so potentially forming the relative less cytotoxic species, such as hydrogen peroxide. So this hypothesis called radical recombinations. So this current trend is flash mechanism is oxygen depletion theory and radical recombination theory as considered an impossible hypothesis. So and many of plausible hypotheses involve the cellular metabolisms and the phenomenon of the occurs mice and human in living organisms. The current situation is that there are still no firm conditions under which the flash effect can be observed in cells. So originally, flash effect has been defined as a phenomenon that occur only in the living organisms, including the mice and human and other animals, and it's considered not to be observed at the cellular level. The site proactive effect induced by ultra high dose radiation in cells is referred to as the sparing effect. So we believe that this definition needs to be reconsidered. Because this is because radiation therapy control is dose delivery to living tissues using the alpha beta ratio, as you know, parameter calculated by this based on the cellular experimental data. Next, Flash, discussion needed to combine this cell experiment to the in vivo animal model experiments, we think. So the University of Osaka group established the ultra high dose rate irradiation system. Using the clinical machine. So this clinical machine can deliver the carbon ion beams. Yes, flash radiation utilized the beam scanning was confirmed as a dose of more 10 gray. About the hematology, hematogenicity plus minus 3% for the beam in the volume of the at least 60 meter, 6 meter in the square feet. So this movie on the right shows the 10 gray and the gray dose rate of 230 gray per second. One field is radiated around 0.04 seconds. We also established the ultra high dose rate proton therapy system. Constructed with the following parameters. So in this experiment, we make the homemade containers where use the increase the number of radiated cells. We needed to use a lot of cells to evaluate the effect of the radiation in case of the higher dose. Our ultra high dose radiation experiment using the carbon ion and the proton beam, we have indeed confirmed the suppression of DNA damage occurs under the ultra high dose radiation. In this figure, you can see these green dots. So green dots represent the DNA double strand breaks, and this number, these dots, is the lower. Under the ultra high dose rate irradiation compared to the conventional dose irradiation. So we can observe the both carbon ion and the proton ion using flash beams. And now, our group has planned to observe the sparing effect of cells under the atmospheric condition using the three kind of radiation sources. By analyzing these results, we can attempting to find the essential mechanism of the flash effect. So this project has already started, and cell experiments has been already being conducted using our facility, L-band LINAC, and we intend to start full-scale experiment above 12 gray, where sparing effect expected. So this graph compares the cell survival dose rate for skin cells using the three radiation types. So red is the carbon ion. The blue represents the protons, and the green represents the electrons. It's highly interesting that the sparing effect appears at the certain dose level. So, for example, carbon ion flash effect we can observe the from 6.5 gray to 10 gray. And in case of the proton, 15 to 20 gray. so we can observe the flash effect. So because so this horizontal axis is a physical dose, and the vertical axis is the surviving fractions. So this you can see that this surviving fraction increase in the case of the after flash radiation compared with the conventionals. Mm. So we have not been able to deliver those. Sorry. So in electron beam experiments, due to the technology still being under development, so we have not yet to be able to deliver those high enough to observe the sparing effect. However, we can seeing the signs in the cell survival rate is gradually beginning to show a gap, and we expected the sparing effect will be likely become observed around more gray, for example, 15 gray to 20 gray, and so on. So on the other hand, so the low dose flash radiation therapy is meaningless. In fact, so low dose flash radiotherapy appearance is meaningful. So this is due to the effect on the invasive capability involved in cancer metastasis. We process advanced techniques for the observing the metastatic potential of the various cancer cells. So we conducted the cellular experiment on the factor related to cancer metastasis at cellular level after radiation. The result shows the invasive capability of cells exposed to ultra-high dose rate irradiation was suppressed compared to those exposed to normal dose rate irradiation. So these cells drive the human breast cancer cells. So this indicates that the cellular response begins even with low dose radiation. It's a highly possible that this anti-tumor effect occurs independently of the direct DNA damage of a cell death. So this mechanism is due to the enhancement of cell adhesion molecule called E-cadherin. So E-cadherin is a protein acts like the glue, holding the cells tightly together. The cells make up our body's surface, and internal organs need to stay so organized rather than scattered. And the E-cadherin helps them stick to the one another to maintain stable tissue structures. When the adhesion becomes weakened, so cells can break apart more easily, which is known that fascinates the spread of the cancer cells. In this way, E-cadherin plays an important role, not only in the maintaining the body structure but also suppressing disease progressions. So Western blotting result shows so this Western blotting means this is a protein level. For example, so black bar is a protein, and you can see that this so normal dose rate 5.6 grades here. So ultra high dose rate irradiation is more bigger this bar. So because expression of the E-cadherin is enhanced. Right? Mm. So in most previous reports, dose was up to 10 gray, and it's possible the dose is not sufficient to observe the sparing effect. So based on our experiments, successfully observing the sparing effect with the two kinds of the radiation sources, we wanted to predict those which sparing effect will occur. So we simply took the ratio like this. Okay, so let's take a short break. Are you familiar with metric known as autometrics? So, unlike a general impact factor, orthometrics indicates the level of social attention that the individual paper receives. In our group, we have successfully and reproductively demonstrated the sparing effect in the cells using the clinical irradiation system. So this work was featured as a web topic by Science, so AAS publisher, which led to the dramatically increase this orthometric score. In addition to the flash effect, I'm also actively engaged in the study on the bone biology and cancer prevention, including the investigation into the anti-cancer effect of the subsequence produced in the brain. I regularly publish a paper journal of the impact factor around 10 or more higher, but you can see that this autometrics only one. Oh no. So this experience made me realize that once again, this flash research is a field that attracting strong social interest. So this many members of the public eager to see this technology translated in the clinical practice as soon as possible, I think. Okay, from here, so I will introduce the latest trend in flash mechanisms. So interestingly, the hypothesis is that previously is considered less convincing is provide so supportive evidence for the two major hypotheses like this and like this. So one is hypothesis is related with the ferrotosis. Ferrotosis is a recently discovered form of the programmed death, cell death, as a pathway indicated from apoptosis, necrosis, and the autophagic cell death. Ferrotosis is characterized the accumulation of the intercellular iron ion and repeat peroxidase. The resulting the oxidant damage ultimately leads to the breakdown of the cell membrane. So this is our ferrotosis. So in other words, this hypothesis process, the radical recombination is very important to this so ferrotosis leading this ferrotosis. Yeah, so for example, so these so radical recombination makes a lot of H2O2. So this result promote this so phantom reactions. Uh, so in this after this result, so ferrotosis will be occurred. So in 2025, the Oxford research group published the important findings that help the bridge to gap between the cell and animal studies understanding the flash effect. So cancer cells are known to accumulate higher level of intercellular iron compared to the normal cells. So in this figure, histology staining images show the lung cancer and breast cancer tissues contains more iron than the corresponding normal tissues. Furthermore, it was demonstrated the high expression of the transferrin receptor. Transferrin receptor related that take the iron is this principal gatekeeper responsible to the uptake. So this iron is associated with poor prognosis. So this research group demonstrated that tissue iron content is increased. Flash radiation also induced the damage via repeat peroxidization. So especially they fed the animal in the iron-rich diet, eliminate the difference in the iron content between the tumor and the normal tissues. So after irradiation, they found the differences in the incidence of the repeat peroxidization between the conventional dose radiation and flash irradiation was abolished under these conditions. Due to this time constraint, I cannot introduce all aspects of this paper today, but this group also demonstrated that inhibited the increase the H2O2 generated by a radical recombination, um, the flash effect. In doing so, they have successfully introduced a new mechanic layer to the conventional understanding of radiation-induced cellular damage. So this brings me to my one summary. So at present, various hypotheses regarding the flash effect are being actively investigated. However, rather than being explained by the single factor, the flash effect is increasingly understanding as integrated outcome of physical, chemical, and biological process induced by the radiation. Therefore, I believe this in the future, the flash effect will be describe the term of the possibility of the current of the proportion of the effect observed rather than the all or none phenomena. So this is a current summary of the status of ongoing clinical trials around the world. So already, two projects completed. So from the Switzerland and the United States. So today, I mainly discuss flash hypotheses. However, unlike the development of anti-cancer drugs, radiation therapy is supported by a lot of existing evidence. At present, it is difficult to establish treatment approaches thoroughly focused on the presence or absence of the flash effect, but the clinical implementation of flash radiotherapy is not fast off. The acquisition of the key treatment parameter such as dose rate or dose and temporal structure of radiation is already nearing complete in the many countries. So whatever or not the flash effect occur will become so clearly via the result of ongoing clinical trial. So many countries already started the clinical trial. So our group also plan to conduct the clinical trial in near future. So based on these clinical trial findings, discussion on the mechanism underlying the flash effect will further accelerated. Ultimately, leads the development of the fully realized flash radiotherapy system, I think. Okay, so thank you very much for your attention. I would like to happy to take many questions or comment after this symposium. Thank you very much.
Thank you very much, Dr. Minami-san, for the insightful presentation on the Balzia Foundation. So let me share back the main slide. So we'll take questions at the end of our presentation. So you may already type the questions on the chat. So later we will discuss that further after all the presentations are done. So next, our next speaker is Professor Jia Hao from Tsinghua University, China. Prof. Jia is a leading expert in accelerator physics and advanced radiation technologies. She's based in the Department of Engineering Physics at Tsinghua University in Beijing. He received his Bachelor of Engineering in 2008 and PhD in 2013 in accelerator physics from Tsinghua University. From 2013 to 2016, he was a Marie Curie Fellow at CERN. His research focuses on the development of electron linear accelerators for medical and industrial applications, advanced radiation therapy technologies, and high power microwave generation and devices. He has published extensively in leading journals, including Physical Review Accelerators and Beams, IEEE Transactions on Microwave Theory and Techniques, and Medical Physics, contributing to innovations such as compact linear accelerators for flash radiotherapy. So his presentation today is titled Flash Therapy Technology. And without further ado, I would like to welcome Prof. Shah. Profile for to start his presentation.
Oh, okay. Can you hear me?
Yes,
Hello?
I can hear you well.
Okay. So thank you very much. I will share my screen. Can you see the slides?
Yes, I can see
Oh,
your slide now.
okay. Thank you very much. Good afternoon, everyone. I'm very honored to be here at this workshop to share our recent work. And I also want to express my thanks to the president and other organizers of the workshop. My topic is the facility aspect of the radiotherapy, flash radiotherapy. My talk today will be divided into three parts. The first topic is the facility aspect of the introduction of the flash radiotherapy. And the second, I will discuss on why we choose X-ray for the flash radiotherapy. And finally, I will introduce the recent developments and some prototype results at Tsinghua University. So what is the flash radiotherapy? As we all know, the flash effect has become a very hot topic in radiotherapy over past few years. Most of the initial studies were conducted at the cell or animal level. The potential clinical benefits is very significant, sparing the normal tissue while maintaining the same tumor control compared to the conventional radiotherapy. But despite of the all excitements, the progress worldwide has been relatively very slow. The main bottleneck is exactly what we are discussing today: the lack of the suitable accelerators or radiators that can deliver in ultra high dose rate under the clinically relevant conditions. If we look at this table, we can see the current landscape of the particle options for the flash radiotherapy, and we can summarize the situation in this table. The proton beams from cyclotrons can achieve ultra high dose rate, and also they have very good penetration depths, but the fast energy modulation is still a challenge. The carbon or the heavy ions from synchrotrons have very good penetration depths, but the beam current of the synchrotron is often very limited. So to achieving the high dose rate is not that straightforward. The electrons machines, they are mainly built by the linear accelerators. They can achieve very high current, so the dose rate is not a problem. But the penetration depth is very limited, unless we go to very high energies. I will introduce that later. The X-rays, on the other hand, have the advantage of very good penetration depths and no need for the energy modulation because it has a very full depth of the coverage. However, the challenge is that current X-ray source cannot easily provide ultra-high dose rate. So each modality has its own bottleneck. Although none of these devices can fully meet the requirements of the flash radiotherapy, the researchers worldwide are still making their best. using of the existing equipments to conduct some clinical trials. While the scope of these clinical trials is often very limited, but they still provide some valuable reference. So let's look at some of these clinical trials. For example, the electrons. Some European countries are conducting the electrons flash radiotherapy on the skin cancer. So it is only suitable for the superficial treatments, for example, skin or other parts. If we want to go to a deeper tumor, we can use protons. But because of the challenge of switching the energy, nowadays the people can not only use the shoot-through beams. It means that we are losing the advantage of the Bragg peak. I believe that one day, if the device once meet all the requirements, the flash radiotherapy, the clinical trial of the flash radiotherapy can progress very rapidly. So let's discuss the facility aspect of the challenges. So for the protons or heavy ions, the main problem is that they need to modulate the energy to a scan on different depths. So the cyclones requires very significant time on magnets tuning or switching. That reduces the average dose rate of some tissues. For example, if the tumor is large, we may need two beams with different energies. So the time of switching one energy to another energy is normally a very long time. For example, more than 200 milliseconds. And if we look at the zone of PTV2, it can be scanned only once, so it has a full flash effect. But for the PTV1, it has been radiated with 2 times. One is higher and another pulse is lower, so it has partially flash effect. But for the normal tissue, which is we want to protect the normal tissue, they be scanned twice, so the average dose rate is low, so it lose the flash effect. So current days, many people are working on the shorten the switching time. Now it can achieve to 15 or 100 milliseconds had been achieved, but it is still not sufficient for the flash radiotherapies. So the next topic is about the electrons. So let's talk about the electrons from the linear accelerators. Electrons can generally go to extremely high dose rate, up to kilo gray per second, or even million gray per second, which is certainly enough for the flash radiotherapy. However, the conventionally Linux was often operate at a 5 to 20 MeV, which limits the penetration depth. If we want to treat the deep state tumors with electrons, we need very high energy electrons, for example, 100 MeV. That is the scope of very high energy electrons zones. We call it VHE. So the challenge shift from the dose rate to achieve compact, clinically practical VHE facilities. And this brings to the size issues. Currently, VHE facilities are very large and expensive, but there are several efforts worldwide to make them more compact. For example, the CERN and PMB, they are working together to developing facilities of 113 MeV accelerators, but the length is about 10 meters long. At Stanford University, they use a very clever way. They use nitrogen-cooled accelerators, so that efficiency of the structures is very high. So it only needs 2 meters of the accelerators to achieve 100 MeV. But this facility is very expensive. The price of the facilities maybe is $100 million. In Tsinghua University, our colleagues are working on a very compact design. It only has 2 meters long and can generate in 100 MeV. There are also other groups, for example, France and Italy. They use the existing facilities to build the VHE applications. And also, there is a new concept of the laser plasma weak field acceleration. It is very compact. To generate 100 MeV electrons, maybe if you use laser plasmas, maybe you can use centimeters, like your fingers, the size of your fingers. It can generate 100 MeV electrons. But the beam current is very, very low. So it's a VHE machine, but the dose rate is so low, so we cannot use it in flash radiotherapy. So the VHE is very promising. The accelerator size and the complexities still a challenge. But I believe that the compact design will be coming soon. For example, the Tsinghua University, we have built this machine in recent years. So after reviewing all the particles, protons, carbons, and the electrons, we are still wait to ask, is there another path? The answer is yes. The answer is yes. Yes, that's that second part. I'll explain why we believe X-ray based facilities might be more suitable and more practical solutions, especially in terms of compactness and the clinical clinical use. Okay, so why X-rays? There are several advantages. First, the X-rays is very accurate. They provide a very narrow penumbra. For example, if you use electrons, because the electrons is very light particles, it can be scattering in the human bodies and make the field wider and wider. And to focus the electron field is very difficult. But for the X-ray, it is very easy. And the second, the X-rays allows a large field and a better conform dose rate. For example, if you use electrons and protons, you may need a scanner to scan, for example, pencil beam scanning, PBS, pencil beam scanning. But for X-ray, there's no need for scanning. It generally have a very large field, for example, 14 centimeters. And the third, because the mainstream of the current radiotherapy, we use X-rays. So for the dosimetry and the shielding, it will be much easier. Most importantly, X-rays enables a very compact and economical solution. For example, if you look at the accelerator size, the X-ray we only need the energy of 6 or 10 MeV. That brings an accelerator size of less than 1 meters. For the electrons, if you want more than 100 MeV, the exercise is 10 meters long machine. And for protons, if you use a superconducting cyclotrons, you can have a facility of about 3 or 4 meters. It's still very large, but for the carbon facilities, it's mostly 20 meters. But if we want to use the X-rays, we will come to the first major challenge, the dose rate. Most currently clinical X-ray facilities deliver about 6 or 12 gray per second, which is only 0.1 or 0.2 gray per second. But if we want to trigger in the flash effect, we need to over 14 gray per second. So we are facing a gap of 200 or 400 times in the dose rate. That means we have 3 orders of magnitudes. That's the first main challenge we need to overcome. Is it possible to generate the ultra-high dose rate X-rays? Yes, it is possible. For example, if we want to conduct animal experiments, it has been already demonstrated worldwide. If you place the samples very close to the source, for example, if you have an X-ray tube and if you place the animals, the mice to the source with only 5 centimeters, you can easily achieve a very high dose rate because the dose rate is inversely proportional to the square of the distance. For example, but for the clinical use, we need a much larger source to X distance, typically 100 centimeters. If we can somehow compress to make a compact design for the facility, we can compress the distance to 70 centimeters. That's almost very, very compact, and maybe the lowest limits of the SAD, the distance. So it is almost possible for current facilities. And we also have a second challenge. It is the multiple angle irradiation. Because even we go to the flash radiotherapy, it is almost not possible for only one angle irradiation. For example, the X-rays, most of the X-rays, IMRT treatment planning, they need 5 or 7 or 9 angles. So if we use the conventional rotating gantry, it cannot rotate at that fast. If we want to do the flash radiotherapy, the operation may be like this way. We turn beams on, it radiates very quickly, for example, on 15 milliseconds. But the rotating of the gantry takes a long time, for example, 20 seconds. So in this approach, the flash radiotherapy is split to multiple pulses, and that causes a problem. For example, if you look at the zoom 1, which the target is irradiated from only a single angle. The tissues received only a single pulse, and the pulse is very high dose rate, ultra high dose rate. It experiences the full flash effect. It's okay. But for the zone 2, the second zone, which is the cross angle area, in this case, the irradiation is split into multiple pulses, and the duration of the pulse is long, for example, 20 seconds. If we look at the average dose rate, it's greatly reduced, and almost comparable to the conventional radiotherapy. That means the overlap regions, it may has no flash effect. So the challenge is, how do we maintain the flash effect across the entire target, not only the zone 1, but also the second zone? So given that gantry cannot rotate at that fast, we can statically deploy multiple angle irradiation. For example, we can use these 2 approaches. The first one is we use one accelerators, but with multiple beams. We use kicker to kick the beam into different beam lines. So the kicker is very fast, so we can do it in a very short time. It's like heavy ion machines. The second, if the Linux can be very compact, we can just simply place the many Linux to statically deploy it around the patient. So the second patient offers a simple control. It controls very easily and better stability. But it requires the accelerator to be very compact and cost effective. That's exactly what we are developing. So I will introduce later. So of course, we are not only the group working on this. In the worldwide, several institutes are working on this. For example, the Lawrence Livermore National Library in United States is developing induction accelerators with 4 parallel beams. And the UCLA and the Radiobeam are working together on very fast rotating VMAT flash concept. The rotating is so fast, it can be rotating within 1 second. And the China academic of engineering physics are exploring the superconducting accelerators for this application, because the superconducting, the current of the beam current can be very high, and the dose rate can be greatly however, the measured data from these all systems shows that if we look at the SAD of a half of a meter, the dose rate is around 15 seconds grid per second, are still below in the 14 grid per second required by the flash radiotherapy. So there is still a big room for the improvements. So let's summarize the challenge we've discussed so far. The first is that we need to increase the dose rate from 0.1 grid per second to at least 400 times. That's almost 3 orders of magnitudes. We can do it. Current accelerator technology allows us to achieve this, but often with a huge machine size. For example, the synchrotron accelerators with hundreds of meters of the dimensions. And also, for the multiple angle irradiation, a fast rotating gantry is almost not possible and not applicable, because the speed and the accuracy is not safe for the clinical use. So that means we need to place multiple radiator statically installed. So therefore, if we combine these two challenges together, it may be a very huge machine size. For example, if a single accelerator is at this dimension, if we place 6 accelerators, you can imagine the dimensions of the whole machine. But if we want to keep the key advantage of X-rays, we know the X-rays machines is often very compact. So that means we need very compact accelerators. So that's the third part. I will introduce our recent developments. So if we look at the first one is the principle of how we achieve the high dose rate. There is a formula for calculating the dose rate at the source surface distance at 17 centimeters. So if we look at the formula, we can see that obviously the dose rate is mainly dependent on the energy. It's a cubic order of the beam energy and times the beam current. For example, if we can use the beam energy, we can bring it up to 13 MeV. For example, the conventional machine is 6 MeV. If we can build it to 13 MeV, that means we enhance the energy at a times of 5. But the cubic of 5 is 100. So we can easily reduce, we can easily increase the dose rate to 14 grid per second. That's very good. But the shielding of this very high energy beam is very critical, because we know that X-ray penetration depth is huge. And also, another annoying problem is the neutron yields. It generates a lot of neutrons. For example, for the 13 MeV electrons, every 300 electrons produce neutrons. That induced a lot of radioactivity. That means after the treatment, you may wait for several hours to wait the radioactivity to decay. So it limits the application. So the widely accepted energy in clinical use is limited up to 10 MeV. But for the 10 MeV, you need we can do the calculation. 1 kilowatts beam power is generate 1.6 grid per second. So we need at least 25 kilowatts beam power, which is still possible for the linear for the current accelerator. Because if we look at the food radiation accelerators, it can achieve the power of 20 kilowatts. So we built a backward traveling wave structures for this ultra-high dose rate generation. We've designed these structures with 1.6 meters. It's still not too long. The structures is optimized to handle the high beam power while maintaining the good efficiency. This should be the world's first system that can use a linear accelerator to generate high dose rate X-rays. At that time, we built this setup with an industrial irradiation LINAC platform. Because the electron beam power for the flash radiotherapy is so high, for example, 250 kilowatts. So to prevent the tungsten target being punctured, we designed a long drift tube. This allows electron beams to be spread out to a large spot size. For example, we spread the beam to about 10 centimeters diameters, which reduce the heat density on the target. Of course, this is not ideal for the therapy because these results are very large per number. But we provide that conventional linear accelerators can achieve a sufficiently high X-ray dose rate, at least meet the flash radiotherapy standards. This gives us the confidence to move forward. Here are our measurements results using EBT3 films. We performed the test at 15 centimeters, both 15 centimeters and 17 centimeters, confirming the generation of the ultra-high dose rate is achieved. The percentage depth dose PDD curves match the Monte Carlo simulation of the 10 MeV simulation. The dose rate at 15 centimeters can be achieved at 18 gray per second and reached about 14 gray per second at 17 centimeters. It already meets the commonly accepted threshold for flash radiotherapy. Okay, so built on this, we have the confidence to move forward. So we developed a more compact accelerator. The previous one, the accelerator is about 1.6 centimeters, but the new version, we compress it to only 16.2 centimeters. It's much more compact. This is mainly because of the improvements of the power source. The power source here is about only 5 megawatts. Nowadays, the power source can be upgraded to 7.5 megawatts. And it gives us a much more compact and powerful accelerators. As shown in the table, the energy is still 10 MeV, but the beam current is much larger. It's about 413 milliamps. It's about 1.5 times of the previous one. This is about only 300 milliamps. So the dose rate at 17 centimeters can be achieved at 72 grays per second. And also we make very big improvements. We eliminate the long drift tube. We use this rotating target because the heat load is very huge. So if we to rotate the tungsten target, it can spread all the heat in a larger area. And after the calculation, we show that the temperature rate, the temperature stays below 600 degrees. And this gives us a high dose rate. And this is an animation. You can see what happened if the rotating target does not rotate. If you can see the heat is so huge, and when the beams on within 1 second, the tungsten it be heat and the melting point. So we need the target to be rotated. So with this foundation, we began developing a clinical prototype machine. This is an animation. As you can see, our system can be installed in a conventional hospital Linux bunker. The machine consists of 5 accelerator, and it also equipped with CBCT imaging to do the IGRT. So after the tumor position is confirmed, the system rotating the angles for the treatment plans and then deliver the entire dose rate in an extremely short time. So our solution is is an array of 5 Linux statically installed around the patient. The angle of the distribution is carefully chosen to be suitable for the most treatment plan. We use 5 angles. For example, it's suitable for MRT with 5 fields. But we know that MRT may have more fields, for example, 7 fields, 9 fields, or 11 fields. And in this time, the facility could be rotated in different fractions. For example, even with flash radiotherapy, we may need many fractions. For example, at least 4 fractions. 4 fractions. I don't believe that the flash radiotherapy will be delivered in future in only a single fraction. So at least maybe 3 or 4 fractions. So in different fractions, we can rotate this gantry a little bit. So that allows 5 angles times the fractions numbers. We can multiply the 5 angles, give us more fields or more angles. More angles. For example, if we have 4 fractions, the 4 times 5 gives us at least 20 angles. So this allows a more optimized in the treatment planning. So here is the exciting part. We have already built the first prototype in last year. So this is our machine. It should be the world's first prototype of a multiple angle irradiation. The diameter of this system is about 3 meters, and the length of the machine is about 2.5 meters. It is compact enough to fit into a conventional radiotherapy bunker in most of the hospital. We already tested the dose rate at the center, at the ISO center, with a source to X distance of 18 centimeters. It already achieved at 14.5 gray per second. So the next plan, we may upgrade it to even a higher dose rate, because nowadays many animal experiments shows that if we want to develop a full flash effect, we may need the dose rate to be higher than 100 gray per second. Okay, so let's conclude. There are still many challenges in accelerator developments for flash radiotherapy. No matter what kind of particle we choose, all the particles, X-rays, electrons, protons, or ions, they have dedicated challenges for each modalities. But we believe that the compactness and the cost effectiveness are the key advantage if we use X-rays. Just like nowadays, the mainstream of the conventional flash, we choose X-rays. So I believe in future, if we upgrade to the flash radiotherapy, the X-rays is still the mainstream. So in Tsinghua University, we developed 2 things. The first one is a very compact S-band structures, Linux, that can generate a very high dose rate X-rays at a clinical practical distance of 17 centimeters. And we also built a 5-angle prototype machine for the clinical X-ray flash radiotherapy, which we've already built and tested. So we are continue to improve the system, and we hope this work will contribute to the making flash radiotherapy to the clinical use as soon as we can. So that's all. Thank you for your attention.
Okay, thank you, Prof. Hao, for that excellent overview of technological innovations enabling flash radiotherapy and also sharing your insight into practicality of achieving the flash effect. We will take questions from the audience at the end of our presentation. So let me share my slide again. So next, we're gonna move to the next presenter. We'll be talking about the detector, which is also crucial in radiation therapy to ensure safe delivery of the radiation. So our final speaker is Professor Hairul Azhar Abdul Rashid from Malaysia. So he is a Professor of Engineering and Rector of UC Tati, Malaysia. He specializes in optical fiber-based radiation sensing and has led pioneering research in dosimetry for high-dose rate and ultra-high dose rate radiotherapy. With extensive experience in both academic leadership and applied physics, he has published widely in the field and collaborates with international partners on advanced fiber optic dosimetry system. So today he'll be sharing insights into the development and application of fiber optics in flash radiotherapy dose measurement. Without further ado, I would like to invite Professor Hairul to deliver his presentation on the fast radiation detector that he's developing. So please join me in welcoming Professor Hairul. So, Prof. Hairul, would you like to share your slides? Okay, I can see your screen now.
Some of our work in optical fiber radiation dosimeters. In this case, particularly for flash radiotherapy. I'd like to first of all thank the organizers for inviting me to present this and share. Looking forward to all the feedback and future collaboration opportunities. First of all, I'd like to introduce our team. We are essentially a fiber optics research group, and we have been looking at different optical fiber components. We started off with more telecommunication, fiber lasers, optical amplifiers. We moved on to sensors. And this particular one, we started looking at medical sensors, optical fiber radiation dosimeters in particular. And we are a small group with some capabilities in design, simulation, modeling, fabrication, and characterization facilities at Multimedia University. And of course, this is in collaboration with several other universities who have similar interests, namely Sunway University, UC Tati in Terengganu, and also our spin-off company, Lumisa. These are some of the optical fiber fabrication facilities, the MCVD facility, and the Pulling Tower, University of Malaya. Yeah. We started off looking at silica optical fiber dosimeters, ones which were doped with different dopants. These are the typical dopants used in telecommunication applications. And we've also looked at undoped optical fibers. And we have been doing this collaborative with several strategic partners since 2015. And we've also looked at different geometries of fiber, not just cylindrical, but also those of flat fiber, photonic crystal fibers, and so on. As far as dosimetry techniques, we started off with thermoluminescence, and we moved on to optically stimulated luminescence for a short bit, and focused most of our time now at radioluminescence as the dosimetry approach. Now, very quickly on optical fiber dosimetry, as you all know, optical fibers have been introduced as a technology mainly for telecommunications, which optical fibers are used to guide light, from one end to the other end for the purpose of communications. Our internet connectivity today, our wireless communications have still using optical fibers in the backbone. Now, the optical fiber comprises of, it's made from silica mainly, and it's made of several layers of core and cladding, both in silica. It has a buffer coating, which is typically polymer-based, mainly for protection purposes. And we started looking at optical fibers for real-time sensing, and in this case, focusing on radioluminescence as the approach. Optical fibers are a good set of materials, high sensitivity, robust, very high spatial resolution, temporal resolution. It's immune to electromagnetic interference. It's impervious to water, making it suitable for in vivo dosimetry. So such a medium or material for dosimetry has pushed us into several applications, from radiotherapy. In further detail, we looked at time-resolved dosimetry. We've explored into industrial radiation dosimetry, and also norm measurements in oil and gas, mining environments, and so on and so forth. So the beauty, or I guess we were lucky for our group, is that we had fabrication characterization facilities giving us access to MCVD and the Pulling Tower, allowed us to fabricate custom-made optical fibers for such purpose. To give you a flavor of one of our optical fiber dosimeter, this is a germanium doped silica dosimeter. Has a 3.5 weight % component of germanium, cladding size 900 microns or so, and a core diameter of 800 microns. Just to give you a feel of what this optical fiber is made of. Now, the method that we focus on is essentially radioluminescence. if you look at the diagram, radiotherapy setup with radiation pulses being exposed to the scintillator or optical fiber. The optical fiber, through the mechanism of radioluminescence, produces light signals in correspondence to the exposure from the linac. And this light intensity is directly proportionate to the dose being delivered or absorbed by the scintillator through the mechanism of radioluminescence, which is essentially an electron hole pair being produced by the ionizing radiation. It recombines and produces photons, and this intensity of the photons being produced is directly proportionate to the dose, the absorbed dose provided by the ionizing radiation. So this luminescence is later on being detected by the photodetector, converted to electrical pulses, and being processed further to some measurement software. And here is an example. For example, we have at 6 MV, 600 MV per minute, a PRF of 400 Hertz, dose of 1 gray, obtained in 10 seconds at Vmax of 1.5 centimeters, where each pulse delivers 0.233 milligray. So this should give you an idea of the optical fiber radiation dosimetry system being used vis-a-vis a radiotherapy linac. So these were some of our earlier results used in the 6 MV, 6 MeV linac. Produced very good linearity with dose rate. And we've moved on to time resolved dosimetry, where we wanted to be able to zoom into individual pulses. We worked with different materials such as cerium dope-niac, cerium and terbium co-dope-niac, cerium dope silica, in partnership with our friends in Shanghai University, in CSIR India. And the aim was to work towards a material whose lifetime is less than 100 nanoseconds and produce high density of luminescence, higher than 3,000 photon counts per gray. So we were then able to zoom in a particular pulse. Yeah. So if you can look at the top left diagram, this is a typical a pulse produced by an 18 MeV electron mode linac. Yeah. So we're able to zoom in and characterize the pulses rise time, decay time, and we are able to profile that single pulse using an NTPC analog output together with a digital oscilloscope. So, focusing on the topic of running a machine measurement in a flash facility, we were lucky to establish connection to Tsinghua University through our friends at the University of Limerick. And this particular flash facility is experimental. It's set up in the lab, available for 2 different energies at 6 MeV and 8 MeV. a pulse width of 4 microseconds with dose rates up to 500,000 grays per second, and has a pulse repetition frequency that can be varied from 100 to 300 hertz for both engines. Here's some photos, diagrams of the setup here. And we used our germanium dope optical fiber dosimeter attached to a polymer optical fiber connected back to the readout unit. Yeah, and we tested it for different doses, different pulse repetition frequencies, with fixed instantaneous dose rate at 500 kilogray per second. So as a baseline validation, we tested out the reciprocity. So this is using a conventional 6 MeV VNAC. We looked at the distance-dependent response of the inverse square law, and we observed the expected inverse square law relationship. Yeah, the signal variation was within 6% of the standard deviation, and this sort of establishes the baseline for flash performance comparison data. We also looked at temporal characteristics of the scintillation signal. So when we zoom into one particular pulse, we can observe the distinct scintillation rise and decay profile. The signal exhibits exponential decay behavior as expected from a scintillator material that we used. And this indicates presence of both fast and slow components. The prompt emission being the fast component and the longer decay tail and the slower component. And this temporal response is consistent with our previous measurements in earlier studies using the same dosimeter, the germanium dope optical fiber. So our first measurements of the germanium dope optical fiber flash conditions, where we varied pulse repetition frequencies from 50 Hz to 300 Hz, with a fixed dose of 10 gray and energy of 6 MeV. Where we can observe very clear pulses, but we also observe at low PRF pulses at 50 Hz. The pulses are clearly separated. And as we move on to higher PRF at 200 Hz, 300 Hz, the decay of the pulses starts to overlap at the baseline, start to elevate. And you can see that we have reduced ability to resolve the individual pulses as the PRF or the pulse repetition frequency starts to increase. We moved on to study the effect of increasing dose at fixed PRF. So we fixed the PRF at 50 Hz. We tested out for 10 gray, in steps of 10 gray up to 50 gray. And we can see the pulse amplitude remains relatively constant, clear pulse by pulse resolution maintained at this PRF. However, we can observe that the baseline starts to gradually increase, and this is most likely caused by the incomplete decay of the previous pulses. So then conclude same as we observed in our first measurements of increasing TRF. Now, one of the key limitations, as we observed by now, is that at high TRF, the interpulse spacing becomes short, and the scintillation signal from the previous pulses does not fully decay, leading to signal overlap or pulse pile-up, and the baseline starts to elevate. Now, the other observation we made was the detector or the PMT had reached a saturation limit of 1,600 count. The true peak intensity becomes underestimated in this case. So the individual pulses become indistinguishable at high PRF of 200 Hertz, all resulting in loss of temporal resolution and a reduced dosimetric accuracy. Now, if we were to make a comparison between the low and high PRF, in this case, we fixed the dose at 50 Gray and 6 MeV, the two different PRFs of 50 Hertz and 300 Hertz. We can see how at 50 Hertz of PRF, the pulses are clearly separated. The decay of the pulses is complete before the rise of the next pulse, and we were able to accurately integrate the area under the pulse for those measurements. But for high PRF, we have overlapping issues at the baseline, truncated decay tails, and leading to eventually an underestimation of the signal. When we integrate the area under the pulse to measure the total absorbed dose, we plotted the RS signal for dose delivered from 10 Gray to 50 Gray for different PRF. The green line is 300 Hertz, the light blue line is 50 Hertz PRF, and we can see that the slope increases with increasing PRF. This is resulting from the underestimation of the signal pulses, resulting from the pulse pile-up and baseline increase. However, at lower PRF, we can see the steep slope, better sensitivity compared to higher PRFs, where the slope is reduced because of the signal loss. When we plotted RL count versus increasing PRF, you can see a drop there in the value. These are all, each line representing different doses. The light blue line is the dose at 10 Gray, and this is at 50 Gray, the darker blue line. As PRF increases, we can see gradual reduction in R squared. Yeah. And at the highest PRF 300 Hertz, we can see R squared is dropped to 0.96. Now, we come back to our earlier observation of the slow and fast components. Yeah. So because of these two components, we did some post-measurement signal processing. The scintillation signal that comprises of these two fast and slow components. At higher PRF, the slow component does not fully decay, and accumulates across the pulses. And this leads to the baseline elevation and pulse pile. So we are taking the approach of deconvoluting the signal into these two parts of the fast and slow component. And we are able to identify and isolate the slow component. We subtract them from the subsequent pulses, and this enables us to remove the baseline elevation and reduce the pulse pile up and the pulse overlap. Now, if we reconstruct the pulse by pulse signal by deconvoluting and deconvoluting into the fast and slow component and subtracting the slower components away and focus on the fast component. For each pulse, we are able to extract a local signal window and apply curve fitting and reconstruct the individual pulses, response, and sum all the reconstructed pulses to obtain the corrected overall. So the approach of deconvolution and reconstruction of the distorted RL signals allows us to successfully separate the overlapping pulses, remove the baseline, and recover the true pulse amplitudes for an accurate temporal structure or temporal measurements of the pulses. And this overall improved dose estimation and pulse by pulse resolution, and especially at higher PRF. So what does this mean to flash radiotherapy? We are able to measure the absorbed dose real time, being able to do this through pulse resolve dosimetry, and we are able to support accurate dose verification in ultra high dose environment. So we foresee flexibility supporting applications in treatment monitoring, quality assurance, and on to in vivo dosimetry. The size of the optical fiber, approximately 100 micrometers, allows or provides for high spatial resolution, suitable for small field and localized measurements. On top of that, of course, the optical fiber radiation dosimetry system allows for remote monitoring and also with very minimal field perturbation. Some insights from our earlier observation, because of the flash producing extremely high signal intensity, we believe that the detectors are saturated at high count rate and distort the fixed signal. And these are very sensitive detectors. PNPs being used early on for lower signal intensity. And this leads to saturation and reduced linearity at higher PRF. So perhaps it is time to look at new or other earlier less sensitive detectors which may be suited for flash application. And trying to balance the two, we need to find an optimized detector that provides a balance between sensitivity and dynamic range. So in conclusion, we have tested our germanium dome optical fiber insulators for analysis, and it has shown strong potential for real-time flash dosimetry. Nonetheless, we've observed at high PRF, pulse pile-up, vector saturation, and baseline elevation. This has led us to also then observe dose underestimation and reduce accuracy, leading us to propose deconvolution and reconstruction of the pulses approach to improve the accuracy. And we see some potential for more work especially in the detector approach, some advancing processing, and also even the materials used for dosimetry. Yeah. I'd like to take this opportunity to thank all our partners who have been supporting and working with us very closely to where we are here today. Thank you everyone for your time.
Okay. Thanks very much, Prof. Hairul, for sharing your work on optical fiber based radiation detector. Very interesting topic for many of us here because optical fiber detector is not yet mainstream detector in the clinic at the moment. So again, I would like to remind audience to share your questions, if any, or if you have any comment on the chat, so that the panel can take up those questions later. Yeah, so that wraps up all the presentation for all our speakers. I would like to thank again all the speakers for their excellent and highly informative presentations. Very interesting insights into the potentials of flash radiotherapy. We are really looking forward to having this technology in the clinic, as shown a lot of promises, as discussed by the presenters. So now we will move to the Q&A sessions. So I still don't see any questions on chat. I mean, is there any questions that you would like to ask directly? We also welcome that. Let's see. Right. Okay. So there is now one question on the chat. If it's addressed to Prof. Jha, Prof. Jha. So I'll read this question. So before Prof. Jha answer this. So your study, this question is from Jayun Chan. Your study examined immune cell changes at day 1 and day 4 post-irradiation. Oh, so I think, sorry, this question is for Prof. Minami because it's on radiobiology, I believe. So, okay, so your study examined immune cell changes at day 1 and day 4 post-irradiation. However, radiation-induced immune effects often involve complex dynamics, including delayed apoptosis, compensatory proliferation, and long-term immune memory. Did you consider extending the observation window to later time points, example weeks or months, to capture the full recovery kinetics of immune cells? Additionally, how do you interpret the confounding effects of cell regeneration already visible at day 4, given that naive T cell depletion appeared more severe than mature T cells, suggesting incomplete recovery? Thank you for the question. So I'll pass it over to Minami-san.
Okay, thank you for your critical question. Our group also conducted the experiment using the flash radiotherapy to evaluate the immune cells system. And our results is no significant difference in the effect between the flash and conventional dose radiation. Other so group also already reported the so immune so in the case of the immune system, so this those rate is not affected, but so our in our experiment, so after irradiation to the tumor cells, so tumor cells after irradiation upregulated the some immune response related protein. For example, this protein is easy to so attack from the lymphocytes. So this some factors is a change upregulated after flash radiation compared to the normal normal dose radiation. But so yes, usually immune system is not affected after flash radiation.
Okay, thank you, Dr. Minami, for your explanation. So I hope that answers your question, Jayun Chen. Is there any other questions for other panels? Maybe can I ask one question to Prof. Shah? I saw that you shared a prototype of your flash X-ray system. So is it currently being used, for example, for animal studies or early clinical trial? If you can share with us.
Okay. The prototype is now being under testing because the dose distribution from different angle is not very uniform. So we are adjusting the dose distribution, and hopefully in the summer we can perform a big animal experiment, something like a pig or dog, because we already had a very small platform for the mice experiment. There is no need to use this huge machine to do the mice experiment. It will be a waste. So it will be better for the facility to perform a large animal experiment. So hopefully after the summer, after we adjust all the dose distribution to a more uniform one, and then we can perform the experiment.
Oh, sounds very interesting. Thank you for sharing that information, Prof. Shah.
Thank you.
So let me look at the chat again, see if there's any more question. No, maybe one question for Prof. Hairul, because I think in Flash, the time is very critical, right? I think you shared earlier. Maybe you can share again what is um, the frequency of the optical fiber system that you're working on. I think because like Prof. Minami shared earlier, it's the in the range of like the response for flash is within like the range of faster than microseconds. So maybe you can share a bit about what your detector can measure the time resolution.
Sure. Thank you, Dr. Hafiz. I'm just going to bring up the slides again. We were testing our scintillators for PRF between 50 Hertz to 300 Hertz. So if you look at this minute. So we were able to resolve these pulses, which were 4 microseconds wide, and at the lowest PRF of 50 Hertz, and we tested it up to 300 Hertz. So we could resolve up to 300 pulses per second. But nonetheless, as I mentioned earlier in the talk, the higher PRF, we could observe pulse pile up. So it's something that we have to work on, either work on a new material which has a faster decay response, or as we proposed and presented earlier, go on a post-measurement signal processing approach where we deconvolute and separate the signals to clean it out.
Okay, it sounds very promising technology. Thank you for sharing that.
Thank you.
Prof. Hairul. So I think there's no more questions from the audience. we are going to open up if there's any additional comment from the speakers, if any, before we end the session. Or from the audience, any comment? Okay, I don't see any. So again, I would like to highlight